let's address a burning question on how many non-measurable sets there are. The book doesn't address this. I'm not exactly sure why, but we've constructed one single non-measurable set. Which might make us believe there ain't that many non-measurable sets. In section 2.6, we use the axiom of choice to construct that non-measurable set. We denoted it as P if we went through the third edition of the notes. In the fourth edition of section 2.6, they used the same construction. They avoided the circle plus stuff, but still, conceptually, it was the same construction. This example, it's everywhere in books on this topic, Lebesgue measure, Lebesgue integration. You always get the same example of a non-measurable set. So what's up with that? Is it the only non-measurable set? Well, you could take translates of it, I guess, and get other non-measurable sets. But it's shown, it's mentioned in some of the notes from the book, by Robert Solovay, 1964, we cannot construct a non-measurable set without the axiom of choice. So totally dependent on the axiom of choice, as we've discussed, that comes with its disadvantages. I don't know anything about actually what's in that non-measurable set, nothing specific. In set P, we knew it had a rational number, but that's all. I don't know which rational number it contains, because we use the axiom of choice in its construction. So we might be led to believe that there are just a few non-measurable sets. You only got one way of building them. Maybe there's not that many non-measurable sets. That'd be good news. That would mean Lebesgue measure is very robust if there's only a handful of non-measurable sets. Turns out not to be the case, but I think it's reasonable to ask the following two questions, the following two cardinality questions. What is the cardinality of the sigma algebra of Lebesgue measurable sets? How many Lebesgue measurable sets are there in a cardinality sense? And secondly, what's the cardinality of the power set of the reals set minus the sigma algebra of Lebesgue measurable sets? That is, how many non-measurable sets are there? We're in the realm here of the power set of the reals. If we assume the generalized continuum hypothesis, then the cardinality of the power set of the reals is denoted at Aleph 2. So good news would be the cardinality of calligraphy M is Aleph 2. That'll tell you there's as many measurable sets as there are subsets of the real numbers. Good news here would be the cardinality of the collection of non-measurable sets is less than Aleph 2, Aleph 0 or Aleph 1. Turns out they're both Aleph 2. So I got good news, there's lots of measurable sets, and I got bad news, there's lots of non-measurable sets as well in a cardinality sense. And we can establish that mostly based on the one non-measurable set we have and the Cantor set. In the body of the notes, we went through and described the Cantor set. So let me maybe streamline this a little bit. We've taken the interval 0, 1 and removed the middle third. That results in two subintervals. From those, we've removed the middle thirds of those two, in blue in this case. That produces 4 subintervals, all of the same length. We've thirdly removed the middle thirds of those 4, producing a total of 8 little black subintervals here between the colors. Next, we'd remove the center thirds of each of those and so forth, producing a sequence of sets, C1, C2, C3. What we'll do is define the Cantor set to be the interval 0, 1 minus all of these colored subintervals, all these middle thirds that have been removed. A good question for us would be, was a Cantor set, is it measurable? Yeah, it's measurable. Its complement is the union of those little C sub k's. Those little C sub k's were all open intervals. So its complement in the interval 0, 1, relative complement, is open. So the Cantor set's closed. Well, it's closed. It's a Borel set, and it's measurable. So yeah, the Cantor set has some exotic properties. Non-measurability is not one of them. It's a measurable set. In fact, let's add up these things that have been removed. First, we removed one subinterval of length a third. Second, we removed two subintervals of length a ninth. Next, we removed 4 subintervals of length a 27th. And what we're doing is removing, I'm looking for a good thing to look at here, we're removing intervals, the sum of whose lengths are a power of 2 divided by power of 3. 2 to the 0 divided by 3 to the 1. The blue gives us 2 to the 1 divided by 3 squared. The green gives us 2 squared, 4, divided by 3 cubed. The 27th is a lengths. So what we can do is add up the lengths of the intervals removed. We get something of the form 2 to the k minus 1 over 3 to the k. That's the lengths. 1 over 3 to the k was the length, and we had 2 to the k minus 1 in what I just described. So we're going through and removing those. So if we take the interval 0, 1, the fact that it's the Cantor set, disjoint union with those C sub k's. The C sub k's were the individual colored pieces. So we get disjointness here. And we define the Cantor set to be the complement of that union. So we know the Cantor set's measurable. We know all those C sub k's are open sets, so they're measurable. So we've got our additivity, nice finite additivity. The measure of the interval 0, 1 is its length. So we get 1 equals the measure of 0, 1 equals. 0, 1 can be expressed in terms of this disjoint union. Additivity will allow us to pick off the Cantor set and the union of the C sub k's. The C sub k's are just open intervals. Countable additivity again. We know the little C sub k's have measured 2 to the k minus 1 over 3 to the k as described. So we'll sum that up. That's a geometric series with a ratio 2/3. I'll bring the 1/3 out, and we get 2/3 to the k minus 1. You get your formula for the sum of a geometric series. Produces 1 over 1 minus 2/3. The ratio is 2/3. The first term is 1. That simplifies to 1. So we get 1 equals the measure of the Cantor set plus 1. So the measure of the Cantor set must be 0. So the Cantor set's a set of measure 0. I think this is probably explained in some of the notes as well. So certainly it's measurable if it's got measure 0, but again, it's a closed set. So I know we've got measurability of it. This is a supplement that's really about cardinalities. We're going to show that the Cantor set is uncountable. And in the notes for section 2.7, I think it is, there's some comments made about this argument. Let's make it a little more explicit. This is a standard way to show the Cantor set is not countable. Cantor set contains all elements of the interval 0, 1, which can be written in base 3, ternary, without using any ones. Now, this may require us to use an infinite number of 2's, but if we'll look at the elements of the Cantor set, 1/3 is an element of the Cantor set. Let's look back at the picture. We had removed everything from 1/3 to 2/3, excluding the endpoints. So 1/3 and 2/3 are in the Cantor set. And then we go through and chop out all that other stuff. But 1/3 and 2/3 are in the Cantor set. Let's represent those base 3 as that sounds weird. Decimals, base 3. Let's represent them base 3. Let's find their ternary, representation. All right. I'll do that just like you do regular decimal expansions. We'll take powers of the base. In this case, 3 to the negative 1 for 2/3. 2/3 is 2 times 1/3. That's 2 times 3 to the negative 1. So the first decimal in the decimal base 3 representation, deci implies 10, so let me abuse the verbiage a little bit. But we get 0.2 base 3 as the ternary decimal representation of 2/3. Doesn't use any ones. Well, how about 1/3? Well, same argument. 1/3 is 1 times 3 to the negative 1, so we get 0.1. But I said elements of the Cantor set can be written base 3 without using ones, and I said 1/3 is in the Cantor set. So what's up with that 1? I also said, it's still highlighted, can be written. So we're going to play a little trick on that 0.1, and we're going to rewrite it as 0.2222222, infinite number of 2's. 0.2 with a bar over the repeating part. That is a ternary representation of 1/3. That's why they can be written. And it doesn't use any ones. Just as you can write base 10, you can write 1 in 2 different ways. You can write it as 1, or you can write it as 0.99999 with an infinite number of 9's. Both of those are the same representation of the number 1, base 10. Same trick here. We've decreased this digit by 1 and followed it up with a bunch of 9's. Well, a bunch of the last number, base 3, the last decimal, base 3. Base 3, you've got 0's, 1's, and 2's. So 2 kind of plays the role of the 9 in this discussion. But indeed, that's an alternative representation of 1/3. So 1/3 can be written without using any ones. Can be. Now use an infinite number of 2's. Just to get the hang of this base 3 stuff, 20 over 27 is 2 times 1/3 plus 2 times 1/27. So what I'll do is take the fraction, write it as something times 1/3 plus something times 1/9 plus something times 1/27. 1/27 should end the story. Treat these as powers of 3. 3 to the negative 1, 3 to the negative 2, 3 to the negative 3. First decimal, second decimal, third decimal. So we get a 0.202 base 3. And this is an element of the Cantor set as well. 20 over 27. So do I see that in a picture? Yeah, there it is right there. 20 over 27 was the endpoint of something removed. That's something in the Cantor set. Actually, what we've removed, anything in this interval, I think we'll state this shortly, anything in the interval 1/3 to 2/3 is must be of the form 0.1 something, excluding the endpoint. I got a trick for the endpoint, but these are all 0.1 something or other. The ones in this interval are all of the form 0.01 something. The one in this interval on the far right are all of the form 0.21 something, base 3. So you get the requirement that the ones are in the decimals of those numbers, the base 3 decimals, representations of those numbers that were removed. And that's explained here in terms of the use of the ones. All right, now about the uncountability. So where we stand is the Cantor set contains all numbers between 0 and 1 that have a ternary representation that may not involve 0's and 1's. It can have a ternary representation that doesn't use 1's. So it's only 0's and 2's. So everything in the Cantor set relates to base 3 expansions that only involve 0's and 2's. So there's a natural 1-to-1 and onto mapping from the Cantor set to the sequence of all 0's and 2's. I discussed it in terms of decimal representations or ternary representations, but I could treat these all as infinite sequences of zeros and twos. Might need to tax an infinite number of zeros on the ends of some of them, but that's okay. Still, it's a sequence of zeros and twos. The set of all sequences of elements from a set of size 2 or larger is uncountable. Well, I've got a one-to-one mapping, one-to-one and onto mapping from elements of the Cantor set to the sequence of all zeros and twos. So the Cantor set must be uncountable. So there you go. It's an example of an uncountable set of measure 0. Let's try this without the reference to the sequence result. Let's give a specific mapping. I'm going to map the Cantor set one-to-one and onto the interval 0, 1 as follows. We can explicitly map the Cantor set like this. Take X to be an element of the Cantor set, so base 3, it's of the form T sub 1, T sub 2, T sub 3, ... a base 3 ternary representation using only zeros and twos. Here's what we're going to do. Let's look at the following number, base 2. Binary representation. Take T sub 1 divided by 2. Take T sub 2 divided by 2. Take these, I just can't help but use the word decimal. Take these decimals in the base 3 representation and divide them by 2. So the zeros up here stay zeros down here. The twos up here become ones down here. So what we're doing is changing all the twos into ones. You had every sequence of zeros and twos up here in the Cantor set. Well, this little mapping simply turns the twos into ones. It means you have every sequence of zeros and ones down here in this list. We'll treat that as a base 2 decimal expansion. So you're getting then all sequences of zeros and ones, 0 point, and then all zeros and ones. Then that's giving you every number in the interval 0, 1 by giving its binary representation. So we're mapping base 3 representations of Cantor set elements to base 2 representations of elements in the interval 0, 1. And we're getting everything. It's one-to-one, it's onto, there's you a specific one-to-one and onto mapping of the Cantor set to the interval 0, 1. You know the interval 0, 1 is not countable, so the Cantor set's not countable, and there's the one-to-one and onto mapping with an uncountable set to prove it. So I draw great pleasure in having an uncountable set of measure 0. And we've made observations along the way that there ain't a very good relationship between cardinality and measure. You know the following. Countable sets have measure 0. End of statement. Well, we just saw an example of an uncountable set that also has measure 0. So cardinality doesn't mix too well with measure. There's not much of a correlation. If a set's countable, it has measure 0. If it's uncountable, it could have measure anything, even including 0. The Cantor set, uncountable set of measure 0. All positive measure sets are of necessity uncountable. That's a contrapositive of the first claim. So not much of a relationship between cardinality and measure, as warned, but this is the first time with a Cantor set that we've had an example of an uncountable set of measure 0. From my measure theoretic perspective, I say that's what's interesting about the Cantor set. Topology folks are interested in the Cantor set for some other reasons I'm not terribly aware of. Among them, it's self-similarity. Well, now we're going to get some mileage out of this Cantor set in terms of the question about cardinalities mentioned earlier. The cardinality of the sigma algebra of measurable sets is the same as the cardinality of the power sets of the reals, is our claim. Using the continuum hypothesis, actually I think it's a generalized continuum hypothesis when I go to Aleph 2, that the power set of the reals has a cardinal number Aleph 2. So what's the cardinality of the sigma algebra of the Lebesgue measurable sets? Allegedly, Aleph 2, the same as the cardinality of the power set of the reals. That's excellent news. There's just as many measurable sets as there are subsets of the real numbers. Well, the proof, given what we have, is pretty humble. You know the Cantor set's uncountable. That is, the cardinality of the Cantor set's aleph 1. It's a subset of the reals, so it'd have to be aleph 1, assuming the continuum hypothesis. Let's take the power set of the Cantor set. Well, the power set of the Cantor set, under the generalized continuum hypothesis, will have cardinality aleph 2. And that's the cardinality of the power set of the reals. Every subset of the Cantor set's measurable. Cantor set has measure 0. We argued that above, elementary argument, in fact. So every subset has measure 0. Every subset of the Cantor set, monotonicity, has measure 0. And measure 0 sets are measurable, as we showed with the proposition 2.4. Measure 0 sets are measurable. So every subset of the Cantor set, of which there are aleph 2, are measurable. So, under the continuum hypothesis, there's just as many measurable sets as there are subsets of the real numbers. The cardinality of the sigma algebra of Lebesgue measurable sets is aleph 2. That's a pretty big jump, and humbly accomplished, because there's aleph 2 measure 0 sets. So we didn't even go to positive measure sets to get this little cardinality relationship. We've made a claim along the way, I think here it is right here, that there's only aleph 1 Borel sets, and you knew the Borel sets are measurable. But there weren't that many, there's alleged to be not that many Borel sets. So we've got good news, the fact that there are aleph 2 measurable sets. There's lots of measurable sets. The Borel sets, all the Borel sets are measurable, but there's only aleph 1 Borel sets. This I don't know how to prove. I suspect it's fairly set theoretic deep, but there's a reference on that claim. So previously, the biggest collection of measurable sets we could describe were the Borel sets, and there's only aleph 1 of those. So not that many as compared to the number of subsets of the real numbers, of which there are aleph 2. So big accomplishment in this observation about the Cantor set. So getting lots of mileage out of the Cantor set. Another claim, now for the bad news. The cardinality of the set of non-measurable sets is the same as the cardinality of the power set of the reals, aleph 2, assuming the continuum hypothesis. So the power set of the reals, set minus the sigma algebra of Lebesgue measurable sets, that is the collection of non-measurable sets, has the same cardinality as the power set of the reals, aleph 2, if we accept the continuum hypothesis related notation. Proof, this is more the idea of the proof, it's a bit informal. We can generate a non-measurable set for every subset of the Cantor set. All we got to do is take that one non-measurable set we had, which is a subset of the interval 0, 1, and union it with one of the subsets of the Cantor set, translated by 1. So I'll keep these disjoint. So take the Cantor set, translate it by 1, take that non-measurable set P that we created in section 2.6 of the 3rd edition of the book we're using, and that'll produce a non-measurable set. The fact that we've used the non-measurable set and we've unioned it with something else, but we've got a disjoint union, the non-measurability of P still causes a non-measurability problem for P union, this other set. That could use some justification, but it's correct, and this is accomplished for every subset of the Cantor set. And there's aleph 2 subsets of the Cantor set. So this collection of sets here, doing this for every subset of the Cantor set, gives us a collection of non-measurable sets of cardinality aleph 2. So, bummer. There's a whole bunch of measurable sets out there. There's as many as there possibly could be in a cardinality sense. Unfortunately, there's a whole bunch of non-measurable sets out there as well, as many as there possibly could be, given that they're subsets of the real numbers. So that's the good news. That's the bad news. And I think these are natural questions to ask. I'm not sure why the book avoids them. Could be because of all this conversation about the continuum hypothesis. But assuming the generalized continuum hypotheses and the use of these subscripted Alice, good news and bad news. Lots of measurable sets and lots of non-measurable sets as well, even though we really fundamentally only know one non-measurable set, that set P we constructed, or sets constructed with similar techniques using the axiom of choice. So that completes the chapter 2 material along with the supplements. So from here, we'll move into chapter 3. Next topic will be measurable functions. So measurability is going to play a role in everything we do in the addressing of Lebesgue integration. It's all the fault of the non-measurable sets. All theorems will have to start out with some hypothesis about measurability. It's driving us to define the very idea of a measurable function as well. So more of that in chapter 3. I will see you there. Have a nice day.